Hi, so this is question number 962, maximum width ramp. So we have been given one array, and for this array we have to find a pair I comma j such that nums of I is less than or equal to nums of j, and then the width of the ramp will be j minus I. So let's look with the example. So suppose for 6, if we take I equal to 0, then for 6, we will find the j such that j should be greater than I. So we will always traverse towards the right of I, and the value of nums of j should be greater than or equal to nums of I. So here for 6, we can only see j that is equal to 2, like only 8 is greater than 6. So our width of the ramp will be j minus I, that is equal to 2 minus 0 equal to 2. Similarly, for 0, if you want to see the width of the RAM, so we can say that when I equal to 1, uh, when moving towards right, for I equal to 1, possible j candidate, all can be the possible j candidate. So we can check with j equal to 2, then our ramp width, I am denoting it with RW, is 2 minus 1 equal to 1, then j equal to 3. Again the condition satisfy that nums of I is less than and equal to nums of j. So again this condition satisfied. So 3 minus 1 equal to 2. So our RW will be, new RW will be 2, and similarly it will be for 4, and then in the end it will be 5 minus 1 equal to 4. So that's how here the output is 4. So in order to do it, we can simply traverse two loops for each element, starting from I, for I equal to 0 till n, and another loop will be for j equal to I plus 1 till n, and wherever the condition, that is nums of I is less than equal to nums of j, is true, we can calculate the ramp width by j minus I, and it will be the max of this. So we have one solution, but it will be of O of n square time complexity, and space complexity will be O of 1. But it will be a inefficient solution since our time constraint are n equal to 10 to power 6. So we will get TLE. So we will move towards another intuition. Okay. So intuition first point, how I am supposed to get the longest sub array in an array. Let's say I have two index, start and end. If I take my start index as 0 and end index as 5, then the length of my array will be 6. If I take my start index as 0 and end as 4, then our length will be 5. If I take my start index as 1 and end as 4, then length will be 1, 2, 3, 4. 4. So the point to notice here is, in order to maximize our sub-array length, we are choosing the leftmost start index and rightmost end index. So from this, one point which we conclude that in order to get optimal answer, we choose rightmost index as end and leftmost as start. So moving to our second point. Second intuition we need to derive from the condition. The condition says that if nums of I is less than or equal to nums of j, then only we will be able to find the pairs which we need, and always I is less than j. So let's understand it with the help of an example. This is our array, and let's start by taking 6 as an starting point of our subarray. When we start with 6 and we move from left to right, but we won't be able to find any element that is greater than 6. So 6 can't be our possible start for our subarray, solution subarray. Now coming with 4, when we start with 4, we are only able to find one element that is greater than or equal to it, that is at index 4. So our answer can be 4 minus 1, that will be 3. Now coming to 2, when we start with 2 and move forward, I can see two elements are greater than 2. So it can be one possible answer. It is also one possible answer since the width of RAM for this 2 and 6 is maximum. We can say that we will be taking 3 as our end element, or 6 as our end index, minus 2, that is equal to 4. So what I want to tell you from this iteration, that if we take the smallest element or a small element, for example, if we consider 4 and 2, if we take 4, the probability of finding a element that is greater than 4 is less as compared to the probability of finding an element that is greater than 2. You understood what I said? I mean to say that it may be that it is not 100% sure, but logically thinking, the probability of finding an element that is greater than 2 can be more than finding an element whose value is more than 2. For example, here we can see that we found 3, but in case of 4, there was only one element that is equal to 4. So second thing which we get from this intuition is that our preference will be given to smaller elements, as the if we decrease the value of nums of I, the possibility of getting nums of j greater than nums of I will increase. So choosing smaller elements. Now moving to our third condition for widest RAM. Okay, let us take an example. Suppose we have fixed our start point to this, and two possible endpoint are there. That means that the value at x is greater than this start point, and the value at y is also greater than the value here. So we can say that if we try to compute the distance between these two, it will be x minus start, and if we try to compute it for this part, it will be y minus start. As we can see, always x minus start is always less than y minus start. So what I have also told it in the first point, that we will be choosing the rightmost index as our ending index. So from this, what we can say, we will start iterating from right to left, from end towards start. That is from n minus 1 towards or to 0. This will be our approach, so that we will never miss this y minus start answer, and we are sure that we will be capturing this. So moving to our fourth point, potential starting point. Now we have to find which all indexes can become our potential starting index for the subarray. So let us take 5 with index 0. For 5, if we see one valid answer is there, that is 6 is greater than 5. So if we say 5 minus 0 equal to 5, this is the ramp width. If we consider 6, for 6 also only one possible answer is there, that is at index 5, 6 is there, equal to 6, 6 equal to 6. So, sorry. Five minus 1, that is equal to 4. So we can see that this 6 is always greater than 5, and here there is a decrease in our maximum ramp width. So the point to be noted here is, if we are at current index with element cur, and if we move towards right, then there is no point in taking or considering a element that is greater than cur and is more than current idx. Let's say it as cur 1. So there is no point in considering that 6 will be a starting point of our array, because always the element which is less than 6 will be, if it is in the left side of the 6, will be our final answer. Like in this case, 5 will be our answer for considering the starting index. So from this, what we can deduce, that the element which we will be processing will always be in decreasing order. Like from point number 2, we came to a conclusion that choosing a smaller element is always beneficial, and here if we are choosing in decreasing order, then only it is beneficial. So what all elements can I choose? 5 can be a potential uh, starting point, and then we move forward, 6 cannot be a potential starting point, then I can say 1 can be a potential starting point. So in case of 1, we can say 1, 1, 2, 3, 4, 5. Again, we are getting 5. So 1 is also a potential candidate. And apart after 1, I don't think there is any other element. So we will do a dry run of this algorithm, and we will be using stack in order to achieve this thing. So from these intuition, let's move ahead to our algorithm. And in order to maintain this kind of behavior, that only we will be putting the element in decreasing order, we will be using stack. So suppose we have created a stack, and we start from here. Since stack is empty, we are putting 6 comma 0 element comma index in our stack. We move forward, we see that current element is less than our stack top, so we can put it here 2 comma 1. Then we move again, we see that current element is greater than stack top, we won't be putting it. Again, 3 is greater than 2, we won't put it on the stack. 4 is greater than 2, we will be moving forward. 5 is greater than 2, no. Now 1, 1 is smaller than 2, it can be a potential start index, so we are putting it in the stack. Then 2, it is greater than our stack top, so we won't be putting it there. And then 3, it is also greater than our stack top, so we won't be putting it here. Okay, so now our stack is ready. Now we will start iterating from left to right. Why left to right? In point number 2, I told you, in order to find, sorry, in point number 3, in order to find the widest ramp, the best cases are where, like ideal cases will be like if we get the last element as our suitable element, like it is greater than our start. So that's why we will be start iterating from the back of the array. So we will be seeing 3. 3 is greater than our stack top, and our condition was nums of I should be less than equal to nums of j. Here 3 we are considering as j, and since it is greater than our stack top, here I will be maintaining a variable ramp width, and I can see that it is greater than our stack top, so I can process it, and the index of 1, sorry, I wrote the index incorrectly, it is 6. Index of 1, index of 3 minus index of 1 gives 2. So currently ramp width is 2. Again, we will see that we will pop it out now. Better way is this. Now again, if we see the stack top is less than our current value. So again, what we will see, the index of our current element 8 minus 1 equal to 7, and since we will be always taking the max, so now our rw is updated to 7. Again we will pop it out from the stack, and we will see now our 3 is less than our stack top, so we will move forward. 2 same we will move forward. None of them satisfy the condition. Now here this condition is satisfied, that nums of j is greater than and equal to nums of I, that is stack top. So here we will again see the index of 8 is 2 and index of 6 is 0, then it will be 2. But since we have to take the max of these two, our final RW will be equal to 7. And like this we will compare with 2 and with 1. Again these both are equal, so we will compare it and we will get 0, max of 7, and this as 0, but again our RW will be 7, and we will pop it from the stack. So this is our algorithm. So our time complexity will be O of n, as we are iterating over the array, and space complexity can also be O of n maximum. Suppose all the elements were in descending order, like 5, 4, 3, 2, 1, then we will be putting every element in the stack. So now let's move to a pseudocode. Pseudocode will be here our function is max width ramp, and we have a array nums. So first I will take n as nums size, then I will take a stack, then I will insert element on in stack in decreasing order, that we call monotonic. Monotonic means either increasing or either decreasing, or something like we are preserving some order. So this is monotonic stack. Then we can initialize a result variable equal to 0. Then we will be iterating for I equal to n minus 1. Like we will be iterating from the back of the index, back of the array, and if current element is greater than stack top, then it is following the condition of nums of j is greater than or equal to nums of I. Here we will do a comparison for our ramp width, and then we will pop the top element, and in the end we will return result. So let's code it out. Yeah, so let's start coding this question. First of all, int n will be num size of the array. Then I will be creating a stack. Now I will be iterating over the loop. And as we discussed, we will be putting the elements in the stack if the current element is less than the stack top or when the stack is empty. So stack is empty, or if nums of st.top is greater than nums of I. So as you have noticed here, I am taking only int, not pair. So this is because only by keeping track of the indexes we can access the element by doing like we have done here, nums st.top. So if it is the case, then we are pushing the index in the stack. Now for the second part, here I have initialized my result variable that is currently 0. Now as we discussed, we will be iterating towards the end of the array. So here I equal to n minus 1, I is greater than equal to 0, and I minus minus. Yeah. Now while our stack is not empty, and if we find a number nums of I which is greater than or equal to nums of stack top, then it will be our ideal case, and we will update our result max of result comma I minus. Here we only need indexes, so we won't be writing nums of st.top, only st.top, and we will be popping out the value return res. Let's try to compile it and run it. Yeah, it is running. Let's try to submit it. Done. Thank you guys.